Hello everyone, welcome back on the course of Higher Surveying, and we are in the module 6 of photogrammetry. Today we are going to discuss about analytical photogrammetry, and the next lecture will also be on the analytical photogrammetry. So we have named two lectures as analytical photogrammetry 1 for today, and for the next turn we have the analytical photogrammetry 2. As we already discussed in the last lecture, that analytical photogrammetry is all about the mathematical treatment of the photogrammetric problems. So in order to understand the photogrammetric from a mathematical perspective, let us first develop the fundamentals using simple mathematics. So let us start with that. So these are the books here. First two books are not going to work, and so we have to look for these three books. The first book, that is Elements of Photogrammetry and Applications in GIS by P.R. Wolf, David and Wilkinson. It is now available in India at low price. So you can easily buy that book. However, for remaining two books, you should join some library, maybe a public library or institute library. In the last lecture, we have learned that how to acquire stereo photos using airborne data acquisition. However, with our all cautions, still there are some errors which are systematic in nature. So before we start a proper mathematical treatment of photogrammetric problems, let us first understand what are the systematic errors there in the acquired photographs, and our images should be first corrected for those systematic errors. These systematic errors are because of lens distortion, atmospheric refraction, earth curvature and image motion. We will go one by one and try to understand what is the importance of each error and how to correct image coordinate. So let us start with that. Lens distortion is also called the objective distortion, and it has a radial component and tangential component. So let us go for the radial distortion. What's the meaning here? Let us say somewhere we have object point and a ray is coming this way. It is passing through the lens, and ideally it should go to this point here. So this is ideal image point. However, because of some defect in the lens, the ray will go to this point here. Delta alpha is distortion in angle, and this is the radial distortion here. The point has shifted from ideal location to this location here. This is the actual image point, and I can measure this actual image point in the image. So this is the distance r, which is radial distance from this principal point here. Imagine that this is image plane, this is lens, this r as a radial distance from principal point, and this is distortion delta r. That means I need to correct image coordinates by delta r, and delta r is given by r minus f tangent alpha, as it is evident from the simple mathematics of the figure. And so once I know the alpha that I can always calculate with the help of r, I will get this delta r. So by applying delta r correction to the image coordinates, image points will be corrected. The radial distortion can be negative, it can be positive also, which means this is positive delta r. Negative means it could be like this. So that will be a negative correction here. That is negative delta r. If there is no distortion in the image, so I have so many pixels, this one pixel, second pixel and so on. So these pixels are the ideal locations. However, because of the negative radial distortion, I will get these curved lines. You can imagine if you have a cushion and we are trying to prick a pin, so some kind of pattern of line is generated. So this is this kind of pattern only, and that's why we call it the pin cushion fact. Similarly, what about the positive one? So this is positive radial distortion. Because of the positive radial distortion, the straight lines will appear bulging out like a barrel, and that's why we call it barrel fact. The radial distortion is given by a continuous function, positive radially outward. This is location of point, and then the correction is given by this model, where all these are some known or maybe determined parameters. So this is new corrected coordinates like this, where these are connection, and this is another condition I assume on this. So I can write this as corrected model. That means this is the measured one, and if I apply all this a0 a1, so I can find out what is x dash. Let us go to the decentering distortion, and it is also called a tangential or prism effect. Because of the imperfect centering of lens and manufacturing defects, this error is there, and this error is asymmetric distortion with respect to the principal point. This distortion shifts the principal point, or if principal point is already shifted, this will further change the pattern of distortion. This is the ideal image plane, which should be vertical here like dotted line. This is the tilted image plane. Because of tilt, principal point has shifted, and as a result, if P1 is a point here or P2 is a point here, it will be image somewhere at different location, here or here. So what's the meaning here? Let us say rays are coming this way, they should be intersected here. However, if image plane is like this, they will reach somewhere else like this, and that is what we call the tangential lens distortion. And this distortion is given by this formula delta x and delta y, where P1, P2 are all coefficients and they are given by this one. So, if you see J1, J2, J3 and J4, they are coefficients of the tangential profile function, and this profile function is given by this formula. And here this tangential profile function is drawn. If I draw a line to that, so it is a tangent here. This is angle phi 0 which we have here. So, we are doing some approximation and we are applying this correction. Now, coming to the atmospheric refraction, we have already talked in basic surveying that atmospheric refraction happens for a large distance. When an aircraft flies carrying a camera, it is acquiring one photograph like this. If there is a point P shown here, ideally rays should follow this dotted trajectory and it should come on the P dash here. Because of the refraction, the rays will go like this, and the image of point P will be here at P. So, this is the distortion here from this point to this point, shown by the arrow here. Now, what is the effect of that? If I draw a tangent line on this curved line of sight, this will touch somewhere here. So, the point that should be here, it is appearing here. That is the effect of that. That means in the height, the elevation of point P is increased because of the atmospheric refraction, and that is not desired. Let us see, there is a r distance on the image of a point. This is a mean sea level, so I am measuring the height with respect to that. So, this correction is given by this value k1 r, k2 r cube plus k3 r5 and so on. We can increase the order. They are called atmospheric k1, k2 constants, and phi is the angle between the refracted ray with plumb line, this angle. We can now calculate values of dr. If I know the values of k1, k2 and k3, and I can apply it to each and every point. Let us look into the correction for earth curvature. Now, if you are using a GPS or any system which is taking care of earth curvature, this correction need not to apply. However, when we do not have the GPS with us, we used to do pseudo 3D survey, where we used to say that we are measuring the heights with respect to the mean sea level, which is a Kurt's equipotential surface, and these heights are superimposed on a map plane in order to indicate the height of a point. The height which are perpendicular to the mean sea level, not the map, and this is done here. Let us see the point P is located on terrain here, and this is sea level MSL. This is another point. This is flying height. This is map plane. Actually, in the field we have acquired this point P, but now we are using the map in order to correct our image. So, the point P, which is measured with respect to sea level, is now projected to point P dash, and that is why instead of point P, we are saying that point P is P dash in the map. And because of that, if I use the map, I will use point P dash, and as a result I will commit some error over there which is equal to this, and this is the error here, ds, and this ds error is pp dash on image, and it is given by this. This is flying height, focal length, s is this distance from n dash to p dash, and r is radius of earth. So, that is the correction we have to calculate to correct our image. So, on the other hand, we have another way. Why can't we correct our map itself? Because P point is imaged correctly. There is no problem with the point P as far as earth curvature is concerned. However, we have measured elevation ZP, and now we are assigning elevation ZP above the map, and it becomes P dash. So, when I correct image with the help of a map, I am assigning P dash point instead of P point. So, let us correct our map, or let us correct the elevation of point P dash. Correction is given by s square by 2r. So, this is the correction we need to apply here, so that I will correct the elevation of point P dash itself, and then either I will do this or do this. Either of the two I can do, and I will correct image, or maybe I can correct map. So it was the earth curvature correction. Now let us imagine another situation where the aircraft is flying carrying a camera. So camera clicks, and the moment it clicks, the scene is acquired. During this time, which is in microsecond for which camera opens the shutter, that is called the exposure time, TE here. Because of the movement of the aircraft, the point which should come here like this is the image, it should come here, it will be shifted because camera is moving this direction, and this point which should come here, it will come here. Again, imagine that point, if aircraft is stationary, it will come here. However, the image is moving like this, and as a result, this by the time rays are reaching, they will reach somewhere else. So there is a distortion opposite to direction of flight, and this distortion is called image motion, or rather image of a point is moving. It is in the motion, and this is given by dm, where delta v is the motion of an image point, and it is given by this formula, where f is focal length, v is the speed of the aircraft, h is flying height, and h is the height of a point which we are trying to image. So now you can see, if I multiply this delta v with the exposure time, I can find out during that exposure time what is the motion of a point which is moving with this speed delta v, and that is the image motion. Nowadays, camera technology, especially for digital aerial cameras, automatically corrects the image motion. So nowadays, image motion is not that relevant from the user perspective. Yes, if you are a company which is working for acquisition of data, you should consider this one. So these are the 4 systematic errors. After that, let us look into some mathematical models of image refinement. What's the meaning here? Systematic error follows some mathematical rule, so we have corrected it. However, there are some errors which always follow some pattern, and those patterns are very much known to us, and according to those patterns, we try to correct our images. We look for such patterns first. So if you find a pattern, then we will immediately use a particular type of mathematical transformation. So these transformations are conformal transformation, affine transformation, projective transformation, and polynomial transformation. So there are some situations under which we use this. Let us look into the generic 2D transformation, which is written like this, where these are corrected image coordinates. This S is scale, R is rotation matrix, T is translation, and X is measured or the observed image coordinates. That means I want to rectify X and Y image coordinates, and I want to calculate X dash Y dash. So I am using this scale, then there is a rotation matrix here, and this is translation matrix. So written here translation, scale, and rotation, and it is happening in 2 dimension only. So let us look into the conformal first. Conformal transformation, preserve the shape. That means the angle between the 2 lines like this is the angle. This angle will be preserved before and after transformation. Let us say you have a tilted photograph and you want to bring it to the vertical photograph. In the last lecture, we have learned some corrections. So we can also do by conformal transformation. For conformal transformation, we assume here that vertical photo coordinates are parallel to the ground. That means xy plane of vertical coordinate system is parallel to the ground surface. Now we will also use the conformal for this purpose, that we will look into the next lecture. First understand how to do the conformal transformation. So let us look into the basic equation again here. I put Sx equal to Sy equal to S. So what's the meaning here? The scale in the generic transformation, when made equal in 2 directions, it is called conformal transformation, which means rotation will definitely happen here by theta angle, but scale in 2 direction x and y will remain same. This rectangle will rotate, scale is same, and as a result this rectangle can be enlarged like this after transformation, or it can be shrinked like this, but still the scale in the 2 direction is same. If you remember the aspect ratio, log aspect ratio in some of the softwares, which means the scale is same in both directions. So this is what is there. Now if I put all this value over there, what will I get? S cos theta into x, S sin theta x0, S sin theta, S cos theta, and here. You can try this equation, write yourself, you will find the same equation. Here S cos theta is there, and this is also there. Similarly, S sin theta is there, and it is minus S sin theta. If I write here, let us say A1 as A2, and let us say A0 here, then I can write here minus A2 and A1, and this is what we are writing here, and this is called the conformal transformation, or you may find this equation in the books also saying that it is a conformal transformation. So, that is the source here of this equation. Moreover, parameters A1, A2, A0, B0. So, total we have 4 parameters here. So, it is also called 4 parameter transformation. So, now let us understand what is the affine transformation. In this transformation, as written on the screen, the shape of the body is not retained. So, what does it mean? Here you can see that there is a rotation matrix which is rotating the body uniformly by angle theta. That means all the points of this rectangle shown on the right hand side will be rotating by angle theta. So, rectangle will still remain rectangle. However, if you look at here, there is a scale factor xx and sy. That means I have different scales in x and y direction. What will happen here? A square may become a rectangle like this. In x direction, scale is sx, and in y direction, scale is sy here, this way. So, now you can see that in y direction and the x direction, so dimensions are changed. Because of this, square has turned into a rectangle. One more factor you can see here, the shear factor. And what is that? Because of the shear, a particular length we can see from this point to this point, it can deform, and because of that, it may take a shape like this. That means a rectangle can further become a parallelogram. So, that is what we understand by the affine transformation. Here we see that translation is also there. So, if I write this equation in this form and if I try to expand the matrix, I will get this equation. So, x dash equal to complete this term here written like this, and y dash equal to this term here. And now you can see here this factor becomes A1, this becomes A2, and this becomes A0. So, this factor becomes B0, this becomes B2, and this becomes B1 here. And so, I can write this equation in order to represent the affine transformation. What happens now? Let us see, this is new axis x dash y dash like this. This is the angle theta, which is represented by rotation matrix theta here. So, that is still only theta rotation here, and then this rectangle has become a parallelogram. So, for changing this thing, I can see here that sxy has played a big role here. And now there is one more factor 0 here, which means that sxy shear is happening only along one direction, not in the other direction. That means we can say that one of the base is fixed and other base is moving. If this is the base, this point to this point is fixed, although scale is changing sx and sy is also changing, but here is happening only in the x direction, and as a result these 2 points are shifting in the x direction. We are having shear here. So, this is the amount of shear from here to here, and this is the shear angle. So, you can see here that the beauty of affine transformation is parallel lines, they still remain parallel. On the other hand, these parallel lines, and they are also parallel here, and that is why we have the 0 shear here, but sxy shear in one direction here. So, that is the role of the sxy here. Now, let us look at projective transformation. So, what is the meaning here? Let us say there are 3 points on an image plane, let us say 1, 2 and 3. Now, say there is a point exists here that connects all the 3 points by straight lines. There is another plane here. So, we are drawing 3 lines in this plane, let us say image plane, this is image plane here, and let us say this is a map plane. So, in case of image plane, I have 3 points, they are coming from one point here like this. These 3 points in the map plane, then they are connected to this point like this, and say there is one more point exists, that is perspective center, and that is connecting these 2 points like this. All the 3 points are connected, that means they are present in both the planes. So, one plane is image plane, another plane is a map plane. So, in the map plane, you can see all the 3 points of the same area. If I acquire the image, 3 points are there. Now, I can do the projective transformation. This is perspective center here, and there is one more relationship happens because this perspective center will also connect to this point like this, and that is called projective transformation. Now, if there is function f1 for image plane and there is a function f2 for the map plane, and if I try to develop some projective equations in 3 dimension, I can write like this, and there I can write like this. So, these are just generic equation for a projective transformation, because generally we write for image plane x y 0, image coordinates, what about capital X bar, Y bar, Z bar here, or maybe capital X, Y, Z, they are object or map coordinates. So, let us see that you are trying to develop image, you are trying to correlate your image with a map. So, you find some common points which are having these coordinates and your image has these coordinates. So, this is the projective transformation because image is one plane, map is another plane. So, now I can use this equation and I can write image coordinates like this. So, f1 x y 0 and map coordinates are x y z. So, I can write x equal to y equal to like this. You can understand it. These are all coefficients a1 to d, and they are called coefficients of the projective transformation. So, how can I find out all the parameters of any transformation? So, in the next lecture we will try to learn how to find out parameters if I have some image points and corresponding to those image points I have map points also. Now, polynomial transformation. This transformation is not for the image rectification, but it is a 3D transformation between the two coordinate system. So, let us imagine that you have developed stereo model using stereo images, and you want to bring the local coordinate of the stereo model in an object coordinate system. So, what will you do now? The simple idea is we assume that XYZ model of stereo can develop some kind of polynomial model like this kind of surface. I will measure some points here in the stereo model, each point is x, y, z. Now, after transforming those stereo models into the object coordinate system, I will get transform coordinates as x dash, y dash, z dash, and so I am fitting up 3D polynomial through this, and these are written as these polynomials 1, 2 and 3. So, once I fit these 3 polynomials for each coordinate, then I can find out any new point. For example, let us say I want to find out these new points here, 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 which I do not know in the field, but now after fitting these polynomial, I will do the interpolation and I can find out the coordinates of these new 4 points. And polynomial transformation is not for the image refinement. So, image refinement is generally done by the projective transformation, conformal transformation and affine transformation. These are the 4 mathematical transformations we have learned now for image rectification as well as for the model development or the model transformation. But there is some physical equation also, or there is some physical understanding also we can develop about our imaging process. For each and every ray or each and every point on the ground surface that is imaged in the photograph. And now, let us try to look that from the perspective of an observer. So, we are trying to understand now the collinearity equation here. So, there is an exposure station L and there is a point P on the ground surface, there is an image and the L dash is the projection of L onto the image, L dash is principal point. So, assume that we have acquired aerial image and we have corrected it for all the systematic error and mathematical errors by transformation. So, I have an ideal image, that means it does not have any distortion. So, as a result there should be some kind of mathematical relationship I can develop. So, let us see this point is imaged at point P like this as shown in the animation. This vector is LP from this point to this point. What about the other vector? I have another vector from point L to point P, this vector. So, I can see here that 3 points, this is exposure station, point P here that is called image point, and this is the point on the ground, or I can say point, they are in one line. I hope you appreciate that concept, it is very simple. Or I can write here that the vector capital LP, which is larger in size, is scaled factor of the LP. So, if I multiply this LP, this one, by some scale lambda, I can get capital LP. So that's the idea, and that is what we call the collinearity equation. That means if 3 points are collinear, I should be able to write this relationship. Now let us see there is an object coordinate system, or it's also written as ground coordinate system in the books. These two names are very, very common. So if you come across any of the term, don't get confused, they are same, object coordinate system or ground coordinate system. Now you can see that this vector LP and this LP may not be in the same coordinate system. So if I bring LP, this vector, into object coordinate system, then I need to have some kind of rotation, what we call as conformal transformation, that we have already done before in module 2. So if I write like that, scale is still there and I need to rotate LP by R. So R is rotation matrix, so I can write like that. So it is representing the collinearity equation only, where R is the rotation matrix, so that both this LP and this LP are in the same coordinate system. If point P is given by xp, yp, zp, now, so I want to find out what is LP, what is LP. So let us try to find out what is LP, this one. This is coordinates xp, yp, zp shown here. So this is yp here, this is xp here, and this is zp here. Similarly, for this point L, I have 3 coordinates xl, yl, zl. In the object coordinate system, I have this vector OP like this, I have vector OL like this, and so I can write OP plus PL equal to OL. O here, O to P, this vector, plus PL, this vector, is equal to this vector. That is simple vector mathematics. I can also write OP, because I want to find out this LP, which is here. So I am writing minus LP equal to OL. So now let us look into this, what is OP and OL, because this is the way I want to find out. So I need to first find out what is my OL and OP. Also I can write here LP is equal to OP minus OL. So this is the way I am writing it. Now let us look into the OL. What is OL? This is OL here. OL is coordinate of L minus coordinate of origin, that is O. So I get XL, YL, ZL. Similarly, I have vector OP. OP means the coordinate of P minus coordinate of origin. So I can write here XP, YP, ZP. Now I can write LP, which is OP minus OL here like this. So I have expressed this vector LP in object coordinate or the ground coordinate system by this. Now I need to find out this LP in object coordinate system. First I develop an image coordinate system to measure this LP from here to here. So why do I need image coordinate system? Because this length is basically expressed in the image coordinates only, because this point P is imaged in the image. First I will measure this LP vector in the image coordinate system, and from there I will transform by rotation to the object coordinate system, and I will scale that transformed LP by lambda, and I will equate to the capital LP here. Let us see L dash, there is a focal length f. I have an image coordinate system small xyz centered at the exposure station, where xy plane is parallel to the image. I also do not know where is principal point, it is unknown. So I have x0, y0, 0. So this is image coordinate system or photo coordinate system. So there are two names, again don't get confused. So this point L dash, principal point, it will have coordinates x0, y0 and minus f, because it is vertically down with respect to the point L, and this x and y plane is parallel to this image plane. So f automatically becomes the perpendicular distance from the image plane, and so I have the coordinate of L dash as x0, y0 minus f. Now what about the coordinate of point P, which is lying in the image plane? And for the point P, it will be xp, yp minus f. So we are measuring with respect to principal point, but I do not know where the principal point is. It could be around center point 0, 0 of the image. So, I have established an image coordinate system at point L, that is exposure station. It is exactly above the principal point of the image, and we know that focal length is the distance between exposure station and principal point. So, this is the f here. So, I developed these coordinates. Now, how can I find out the LP? Okay, LP is the coordinate of P minus coordinate of L. So, coordinate of P and coordinate of L is this, between L to P, and I get it. So, that is the image coordinate of point P in image coordinate system, LP in image coordinate system. It is still not in the object coordinate system. I need to bring it, I need to rotate it. So, I need to apply a rotation matrix, and this rotation matrix is given by Rx, Ry and Rz rotations, such that these 3 rotations in sequence will bring the image coordinate system parallel to the object coordinate system. So, I do not comment anything on omega phi kappa. When you really do rotation, you have to imagine those values first, and also you can change the order of rotation if you find it is easier for you to apply some other sequence of rotation. Use that, no problem. Let us say that you brought LP from image coordinate system to object coordinate system. That means both are in the same coordinate system now. So, I can easily write the collinearity equation. The collinearity will be like this. That means this is function of lambda times rotation matrix and this, where R is given by this, and if I write 3 by 3 matrix, so R11, R12, all 3 by 3 elements here, where Rz is this, R phi is this, and Rx is this. So, we have now established collinearity equations, but there is a small problem here. In fact, we measure the image coordinates and not the ground coordinates. They are ground coordinates or the coordinates of point P or point L in the object coordinate system. I am interested to do measurement on the image. I will now express this coordinates as my output, as my derived coordinates. I will take an inverse, I will write 1 upon lambda here, I will take R inverse matrix and I will write in this form. And now I will call M matrix, which is R inverse here, and this 1 upon lambda is S. So, whatever element I get, they are called M11, M12, M13 and so on. Fortunately, this R matrix is orthogonal matrix, which means if I take the transform of the R, I will get its inverse like this. So, as a result, I am writing the transform RT here. So, it is very easy if you know the R matrix. And remember one thing, it is very crucial, because we imagine omega phi kappa as the conversion from image coordinate system to object coordinate system. We have our imagination that way only. So, these matrices are developed using values of omega phi kappa from image to object coordinate system, not other way around. We have started from there because it is easy for us to understand, and also we have so many images and we have to rotate each image in one object coordinate system, so that we can develop our 3D model in one object coordinate system. So, now if I write these 3 equations 1, 2, 3, I can write like this, xp minus x0 equal to something like this, similarly this and this. You can try it yourself. This scale factor is still unknown. I do not know what is the value here, even because I was not knowing what is lambda. So, I would like to remove it. I will make the ratio of xp and f. That means, I am dividing this equation 1 by 3, both 1 and 2 by 3. So, I will get this equation as a ratio of equation 1 to equation 3. Similarly, this is ratio of equation 2 to equation 3. So, I can get this one where I have removed the scale factor, and these 2 equations are known as collinearity equations, and that is a fundamental governing equation in the photogrammetry. So, one more condition is possible now, the coplanarity equation. So, let us imagine that we have acquired 2 images, that means stereo pair. So, this is the image, let us say left image here, and this right image here, and this is the point P here on the ground surface. and it is being imaged at point P1 and P2. That means point P is coming in both images. It is imaged in both images. So, what is the distance between the two exposure station? Let us call L2 and this is L1 station. So, these are the coordinates here. So, I can now write the collinearity equation for this LP1 is the L1P is, let us say, lambda 1 times L1 capital P. Similarly, I can write collinearity equation here. So, I can write L2 P2 here. So, lambda 2 times L2 capital P like this. See very carefully, if point L1, L2 and P are in one plane, because 3 points are always connected with a triangle. 3 vectors, B vector, L1 P vector, L2 P vector here. So, all these are creating one triangle. And what about the volume of a triangle, which is generally we calculate volume by 3 vectors like this. So, I can write this volume, and volume of a plane is always equal to 0. And so, this is A1 vector here, what I am writing here is L1 P, and here it is L2 P. Now, using the collinearity equation that we learned, I can write L1 P in terms of image coordinates of left image. Similarly, I can write L2 P in terms of right image coordinates like this. So, I am writing A1 as U1, V1, W1 using some transformation, that is M matrix. I am writing first image coordinate here, and secondly it is the second image coordinate here. So, I should write it with our convention R2 T and here R1 T. See, I got this U1, V1, W1 and U2, V2, W2. That is the object coordinates of these points. So, it is first image or what we call as left image, that is second image what we call as right image. So, I got this B matrix as Bx, By, Bz like this, and A1 matrix, A2 matrix. So, if I put like this, I will get this determinant equal to 0. Refresh your 12th standard matrix knowledge, you will get this one, and this is called the standard coplanarity equation. So, because it will lead finally to 3 equations, so we call it coplanarity equations. Now, we understood what is the coplanarity and collinearity. Apart from this, we also talked about the systematic errors in the images, and then we have also talked about the image refinement, and we have also discussed about the polynomial transformation today. So, let us stop here and try to imagine what we have done in case of collinearity and coplanarity, and how are they different. How can I say that they are physical models? If you remember, we have done some rotations and some translations. So, I call exterior orientation parameters, and then we have interior orientation parameters. Let us call the interior orientation parameter first. So, if I know the focal length or the principal distance, principal point coordinates x0, y0, focal length is f here, and parameters of lens distortion. So, I can find out what is the relationship of the image in the image coordinate system. That is what is the focal length, how image is placed, okay, what is the orientation of this one. So, I can say that all bundle of rays, they are creating one image, and as a result all bundle of rays will have these common parameters, focal length as well as principal points. Secondly, once I know these parameters, then I can reconstruct image, or I can reconstruct camera model, and that is why it is called the sensor or camera characteristics. They are also called the sensor model. So, moment I say that what is the sensor model, that means I am asking about these 3 parameters x0, y0, f for a particular image which is acquired with a particular camera. So, these will remain fixed if camera is fixed, and that is why they are called sensor model or they are called camera characteristics. So, once I fix these, camera is known. We have done some image transformation, or we have rotated our image into the object coordinate system by some angle omega phi kappa. We call them 3D orientation. That means we are rotating each and every bundle of ray which are creating the image. So, I am rotating by angle omega, phi and kappa. All the rays are creating one image, and as a result I say that I am rotating an image. These rotations are omega, phi kappa. That means I have rotated image by this angle omega phi kappa. Not only that, I have done some translation here by XL, YL and ZL. In this matrix, XP minus XL, YP minus YL, ZP minus ZL. So, I have translated XP, YP and ZP by this. So, this becomes vector LP. So, these are the coordinates of point L. So, that is why these are also the 3D position. They are called positional parameters or they are called altitude parameters. Orientation parameters are called attitude parameters, and they are basically developing the relationship between image and the object coordinate system. So, this position and orientation, if these are known, I can orient an image into object coordinate system, and that is why they are called exterior orientation parameter. So, they are quite different from interior orientation parameter because interior orientation parameter fixes the camera and image relationship. That means how a camera will acquire an image, so in what position it will be there, what is the position of principal point, what is the focal length. On the other hand, exterior orientation parameters, they are going to develop a relationship between image and the object coordinate system. So, if I have n number of images and each will have different exterior orientation parameter, so if I bring each image into one coordinate system, what will happen? I will need these 6 parameters for each image, and that is why they are called exterior orientation parameter, and they are no more dependent on the camera. So, let us imagine that you have one camera and you are acquiring some photo like this, like this, like this. So, each image that is acquired from your camera will have different exterior orientation parameter according to your position and according to the orientation of the camera itself or the image. At the same time, your interior orientation parameters remain same for all 3 images because your camera is same for all these terms. Let us say you have a mobile phone. So, you are acquiring n number of images from mobile phone. So, all n images will have same sensor model or they have same camera characteristics. At the same time, each image will have different exterior orientation parameter. So, here we stop and we conclude that we have learned the coplanarity equation and collinearity equation, which are the physical relationship between the imaging system and object coordinate system. Secondly, we have also talked about the transformations which are mathematical in nature, and then we have also learned about the systematic error on the vertical images or the vertical photographs. So, with this we stop here and we will meet in next lecture with the mathematical treatment on these equations. So, till then, wait and bye. Thank you very much.